All right, so let's do an example. So calculate the binding energy of helium-6. Okay, helium-6. All right, so there's our formula. So the binding energy is Z times the mass of hydrogen plus number of neutrons times the mass of neutron minus the mass of the atom times that nice conversion factor, 931.49 million electron volts per U. Okay. So now we just have to look it up. Now we just have to use that Appendix C, just look things up. So let's do that. Okay, so let's see. So this is helium-6. Okay, helium, what's helium? Helium is 2 protons. So Z for helium is 2. So we have 2, right, so Z for helium is 2. Okay, what's the mass of hydrogen? So the mass of hydrogen is right here. The atomic mass of hydrogen right here. Yeah, you got to keep all of these significant figures when you do these calculations. So 1.007825. And again, these are in U's, right? So U, right? And then the number of neutrons. Okay, this is helium-6. So 2 protons, but it's helium-6, so there's 4 neutrons. So plus 4, then the mass of a neutron, right here, this crazy thing, 1.008665 U. Oops, sorry. And then, I should have written smaller. And then minus the mass of an atom. Okay, here's the mass, the atomic mass of helium-6. 6.018886 U. Right? And then we multiply that by our conversion factor, 931.49 million electron volts per U. Again, the U's, goodbye, 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 goodbye. I promise you, when you multiply it out, you get 29.27 million electron volts. Okay, so there you go. Now, something that's really important. When we did we looked at the energy diagram for hydrogen. Look at these energies. 14 electron volts, 3 electron volts, 1.5, like 1, all electron volts, right? All electron volts. So in other words, if we wanted to kick this electron up here, just have to give it like 10 electron volts or something like that, right? Here you give it like 2 or something. But all I'm saying is that for the electrons to go from one energy level to another, it's like electron volts, right? Electron volts, because that's atoms, right? Atoms, electron volts, okay? That's chemistry, right? Electrons, right? And so you have electron volts. Now, look at nuclear physics. We're calculating binding energies. Look at these values. Helium-6, we just did that, 29 million electron volts. Uranium-238, almost 2,000 million electron volts. So what's the huge difference between chemistry, where you're dealing with electrons, and they're circling the nucleus, and nuclear physics? Chemistry, with electrons, you have electron volt energies. Nuclear physics, you have millions of electron volts of energy. So it's a factor like of a million. Okay? That's important, and we'll talk more about that in a little bit. Okay. All right. So this is a plot of binding energy, but it's not. Okay. Careful. it's binding energy per nucleon. So here, you know, this was the binding energy for what, helium-6 or something like that, right? Yeah, helium-6, right? So if I wanted the binding energy per nucleon, how many nucleons are in helium-6? 6. So I'll divide that by 6, right? So it'd be like 5 or something like that, okay? So this is binding energy per nucleon divided by the mass number, A, you know, number of protons plus number of neutrons. What do you notice? Yeah. What do you notice? Well, I mean, there's kind of a pattern, right? For these really small mass numbers, you know, okay, first of all, if you want to be stable, if you want a super stable nucleus, what do you want? You want the largest binding energy per nucleon possible, right? Okay, so you want large binding energy. So these guys are the stable guys, right? These guys are not so stable, neither are these, okay? Okay. Now, you know, I mean, they're mostly around like 8 or 9, right? MeVs per nucleon. But anyway, let's just look at this particular section of the graph, okay? So we're just looking at it over here, all right? So what do you notice? I mean, there's a peak here, and a peak here. So that means that this helium is super stable, right? It has a lot of binding energy per nucleon, so it's going to be hard to bust up. So this helium-4 is super stable, carbon-12 is pretty stable, oxygen-16 pretty stable. Why? So we've got to explain that later on, right? We've got to explain that, and we will, don't worry. All right, we've got to explain that. Okay, so again, if we, you know, the greatest stability means the highest binding energy per nucleon. So which isotopes have the highest binding energy per nucleon? So just look at the graph, you know. It's up here, right? Like iron 56 and nickel 62, right? These guys have the highest binding energy per nucleon. So they're going to be the most stable. Okay? We got to explain that too. All right. Now look at these. Look at hydrogen 2 and lithium 6 and beryllium and all that, boron. If they want to get more and more stable, right? They want to move up the chain, I guess you could say, right, up the graph. If they want to become more and more stable, what do they got to do? What are these guys got to do if they want to get up there? They got to combine, right? You know, because it's, look at 2, 6, 9, 11. If they want to get up there, they got to combine, right? They got to join together. And that's called fusion, okay? Fusion. I already talked about fusion with the stars, right? So if these guys want to become more and more stable, they got to fuse together. So they move up the graph. All right. Now, how about over here? And here you have 238, 209, 197. So if you want to move up the graph, no, see here, when we move up, we get a larger A, right? Here, if we move up the graph, we get smaller and smaller A. So what do these isotopes have to do to increase their stability, their binding energy per nucleon? They got to bust apart, right? They got to break apart. And that's called fission. So these are the major forms of nuclear energy, and we'll talk about them sometime, right? Fusion, combine, and fission to break up. Okay, now here's another way to look at this whole binding energy thing, fusion and fission and everything. All right, so, and this is like a review question based on relativity. All right, so here's one type of fusion. This is what happens in a star. So we have 4 protons fusing together to form a helium, 2 protons and 2 neutrons. When this occurs, energy is released, right? So why does fusion of hydrogen release energy? And I gave you a hint. All right, so everybody pause your video and figure this out. You should be able to do this if you remember relativity. Okay. What's the answer? If we're going to produce energy, that means that the mass of this has to be greater than the mass of that, right? Because some of the mass was converted into energy, V equals mc squared. Okay? So what we're saying is that the mass of this, okay, this is just the same thing, right? 4 protons or 4, we're just looking at the nucleus. So 4 protons or 4 hydrogens, just the nucleus, right? Same thing, right? So we're saying that the mass of this has to be greater than the mass of that because that missing mass has been converted into energy. So that's number 2, right? The mass of a helium nucleus is smaller than the mass of the 4 protons. This is a very important principle. You want to remember this, right? If you want to produce energy, this has to have more mass than that. Super incredibly important. All right, let's see. Okay, so another way to look at this fission-fusion thing, which is very useful, is to look at, instead of, okay, so the last one it said energy per nucleon, right? Well, let's switch it. Let's say, instead of energy per nucleon, let's say mass per nucleon, all right? Because, you know, energy is related to mass, right? So mass per nuclear particle, okay? So, so no more binding energy, right? No more binding energy. Now we want just the mass per nuclear particle. So look, so hydrogen has a lot of mass per nuclear particle, correct? So that means when it fuses to become helium, it's going to, you know, there's a big mass difference, right? Mass of hydrogen is a lot bigger than the mass of a helium, right? Right? And so when you do fusion, hydrogen to helium, there's a lot of energy being released, right? When helium fuses to carbon, there's a little bit of energy being released. Carbon to oxygen, a little bit released. Oxygen to iron, a little bit more released. But all I'm saying is these are all fusion reactions because this has more energy per nuclear particle than this. This has more energy per nuclear particle than that. So when this becomes that, it releases energy. When that forms that, releases energy. That releases energy. Okay, look at fission. So uranium has more mass per nuclear particle than lead. So there's going to be energy released, right? Because this is higher than that. When lead becomes iron, there's going to be energy released, okay? So that's good stuff. Now here's the problem. What's the bottom? The bottom is iron. Can iron undergo fission or fusion and release energy? No, it can't, right? Okay, so once you have all these different fusion reactions, you get to iron and you're stuck. Once you get all these fission reactions, you get to iron and you're stuck. Nothing happens after iron, okay? Now you say, who cares? Well, let's learn some astronomy. I promised you we would talk about this. All right, so as I said before, stars are formed from gigantic gas clouds, gigantic things, right? And you know, the gas clouds are made up of hydrogen, a little bit of helium, and they have mass, so there's a gravitational attraction, and so they contract, right? Because there's a gravitational attraction, so they contract. And remember we talked about this with angular momentum in physics 121. They may be spinning just a little tiny bit, and as they contract, their rotational inertia gets smaller, so their omega, their rotational velocity has to increase, so they start spinning faster and faster. But we don't care about that now. We just care about the fact that you have a gigantic gas cloud and it's contracting because of gravitational attraction. Okay, so, you know, energy conservation, as you know, you drop something, what happens to it? The kinetic energy increases, right? So as this gas cloud contracts, the gas particles get more and more kinetic energy, right? And then you have these fast-moving gas molecules, like in the center, for example. They're smashing into each other, right? And so that kinetic energy is forming thermal energy. So basically, what's happening to the center of the star? It's getting, as the star contracts, it's getting hotter and hotter and hotter. All right, great. Now, eventually, when it gets super hot, like millions of degrees, fusion begins, okay? Fusion begins. And for the first time, there's forces pushing the star out, basically to balance gravity. And so the star becomes stable, right? This is a stable star, okay? So you have the fusion forces pushing out, you have the gravitationals pulling in, and they have equal magnitude, so you have a stable star. Okay, awesome. Now, here's what happens initially. This is the first fusion reaction for a normal-sized star like our sun. It's called hydrogen fusion. So the 4 protons fuse to make a helium, and then you have all this stuff given off, okay? We don't worry about all the details. Okay, now eventually, this is mostly a hydrogen gas cloud. Well, eventually, all of the hydrogen, in other words, the single protons, right? Eventually, all of the hydrogen is going to be fused into helium. And so when you have no more hydrogen left, what's going to happen to this reaction? It's not going to happen, right? Because there's no more hydrogen to fuse into helium. Okay, so then what happens then? What happens then is that the helium begins to fuse into carbon. Eventually, all the helium is gone. So then what happens? Well, then the carbon fuses into other things. Okay? So this is kind of what happens. All right? So you start off with a hydrogen fusion, then helium, then carbon, then oxygen, then neon, then magnesium, then you have silicon, and then you're at the end of the rope. So in other words, this forms iron. So we have this iron core. It looks like an onion, right? So then you have this iron core. Now wait a second. Iron can't fuse, can't fission, can't fuse, doesn't do anything. Agree? So once you get to this point where you have this iron core, what happens? Well, there's no more fusion. So there are no more forces pushing the star, counteracting gravity, right? There's no more outward forces counteracting the inward pull of gravity. So then what's going to happen? If you don't have any more outward forces, but you have the inward forces, what's going to happen? The star is going to collapse. Okay? So the star collapses, and bingo! If it's a really, really big star, you get a supernova. Okay? This is only for high mass stars. In a supernova, you either get a black hole or something called a neutron star. But all I'm saying is that, I don't know the history that well, I'm sorry, but I can imagine, so I'm just pretending I know something, right? The astronomers figuring out, well, golly, how come nothing happens after they get the iron core? And then they talk to their physicist friend, and the physicist friend says, well, don't forget, once you get to iron, there's nothing lower, right? You can't fuse or fission once you get to iron. And so it's at the end of the road. So what I'm saying is that the nuclear physics is a great, it explains this. It explains why the star collapses once you get the iron core. So that's kind of cool. All right, let's get back to this nucleus. I keep saying that the nucleus, sometimes the nucleus is stable, all right? Now, and I showed you the graph and all that stuff. This is totally ridiculous. The nucleus shouldn't be stable. The protons have positive charge. All of these protons repel each other. The neutrons have no charge, so they just kind of sit there. But the protons are repelling. So why would this thing be stable? It should blow itself apart with all that repulsive forces from the protons, right? Well, I'm sorry, but Mother Nature, you know, it shows there are nuclei that are stable. Well, what does that imply? It implies that there has to be another force in addition to the electric force, right? There has to be some kind of a strong attractive force holding these things together. That's stronger than the electric repulsion force, okay? Now, wow, that's cool. What are we going to call it? Well, how about the nuclear force, right? So it's called the nuclear strong force, okay? The nuclear strong force. And it's kind of an interesting force. It has a really, really short range. You know, like gravity, right, has pretty much an infinite range, right? I mean, look at, you know, the sun makes us go around, you know, circle the sun, right? I mean, you know, the gravitational force has very long range, you know? But the nuclear strong force has a super, super short range. It only works within the nucleus, 10 to the minus 15 meters or so. Okay, so it's an attractive force, right? We've got to keep that nucleus stable. It's an attractive force, and it doesn't care about the charge. So that means that neutrons also exhibit this strong nuclear force. So here we have a neutron and a neutron, right? They're attracting, okay? We have a neutron and a proton. They're attracting. Now this is a cool one, right? We have a proton attracting a proton with the strong nuclear force, and we have them repelling with the weaker electric force, right? There's no electric force here because there's neutrons. There's no electric force here because there's a neutron. There's an electric force here, right? So the attractive strong force is the same for any two nucleons. We don't care about the charge. But if you have two protons, they also experience a smaller electric repulsive force. So I kind of think of it as like a Velcro, you know? Because again, this has a really, really short range. So with Velcro, you know, let's say here's a piece of Velcro, here's a piece of Velcro. If you have them this far apart, nothing. Still nothing. The force, the attractive force, only gets large basically when they're touching, right? Or like glue or something like that. So that's what this strong nuclear force is. It's kind of like this. Let's say this is the strength of the strong nuclear force, and this is the distance, right? So it's like super, super strong, and then it goes to zero, you know, where this is like the size of a nucleus, okay? Super strong, and then zoop, zero. All right. Okay, so now we can answer a question. All right. So this is the n equals z line, but this is the data, right? These are the stable nuclei. So the stable nuclei have more neutrons than protons. Well, now you know why. Because the more neutrons, the more what? The more strong nuclear force, right? The more strong, okay, all right? So that's why you have more neutrons, because remember, the protons are repelling. But if you have a whole bunch of neutrons, then you get more and more of that strong nuclear force. So that's why you have more and more neutrons here, okay? Does that make sense? All right, let's quit.